Hello dear students, today we are going to discuss about the important topic electric field due to a uniformly charged non-conducting disk. Okay, electric field due to uniformly charged non-conducting disk. Non-conducting means charge not transferred from one region to another region inside the disk. That is called non-conducting disk. Okay, and which is uniformly charged. Let us suppose this is the disk and which is having uniform charge density sigma. Charge per unit area is sigma, and this is the charged disk. The charged disk having radius capital R. R is the radius of the disk. Okay, so our aim is to calculate the electric field with respect to the charged disk at any other point, at any point along the axis of the disk. This is the axial line. Suppose we are going to calculate the electric field at point P. So because this is uniform charge distribution, we take a small portion on the disk and we calculated the electric field with respect to disk at a point P, and later we will integrate to the limits. So a small portion means a small area. Let us take the small area small thickness. This is the shaded portion is the small thickness, that is dr. The thickness of the portion is d small r. That is the thickness of the portion, and this is located at a distance small r from center O. So first we calculate the electric field at point P with respect to the thickness dr with respect to the ring. Already we know the electric field with respect to the ring along the axial point at a distance x from the center. This is the line which is joining the portion dr to point P, and the distance here is root r square plus x square. Okay, so our aim is to calculate the electric field at point P with respect to the entire disk, but in place of that we choose a small portion in the disk initially, and later we will integrate to the total portion. So first we choose the small portion having thickness dr, a circular portion on the disk, and which is at a distance r from center O. So with respect to the portion, the electric field at point P, with respect to the portion, the electric field at point P, we know the relation K into dq into x by r square plus x square whole power 3 by 2. So already we know with respect to the ring, the electric field at point P, that is dE is equal to k dq. dq is the charge of the ring, whatever we choose here, the ring having thickness dr, the charge on the ring is dq, the portion, and this is the small charge. With respect to the small charge, what is the electric field at P? Already we know, we calculated the electric field with respect to the ring along the axial line, which is dE is equal to k into dq into x by r square plus x square whole power 3 by 2. So what is dq? So dq we are going to write in terms of the charge density. Charge density is charge per unit area. Charge per unit area. Area means circumference into thickness. Circumference is 2 pi r, thickness is dr. So dq is equal to sigma into 2 pi r dr. That is dq. So dE is equal to k into dq means sigma 2 pi r dr into x by r square plus x square whole power 3 by 2. Okay. So to calculate the total electric field, we integrate the portion dE. So by integrating on the both sides, by integrating integral of dE is equal to k into sigma into x into 2 pi into 2r dr by r square plus x square whole power 3 by 2. In integration from the limits 0 to the total radius r, this is 0 to e. So this is the integration part. So integral of dE is equal to e. Integral of dE is equal to e, and k into sigma into x into pi. Then let us suppose r square plus x square is equal to z. Let us take r square plus x square is equal to z. So then dz is equal to 2r dr. To get the simplification process in the integration, we take r square plus x square is equal to z and dz is equal to 2r dr. So that numerator 2r dr is equal to dz and denominator z whole power 3 by 2, because r square plus x square we take it as z. So integral of dz by z power 3 by 2, it is very easy to do that integration. That's why we take z in place of r square plus x square. So E is equal to k sigma x into pi z power minus 3 by 2 plus 1 by minus 3 by 2 plus 1, and integration limits are 0 to r. So that minus 3 by 2 plus 1 k into sigma into x into pi into minus 3 by 2 plus 1 is equal to minus 1 by 2, that is minus 2, and z power minus 3 by 2 plus 1, that is equal to minus 1 by 2. Z power minus 1 by 2 means r square plus x square whole power minus 1 by 2. Minus 1 by 2 is nothing but root. This is root. One by root r square plus x square. The limits are 0 to r. So that E is equal to minus 2k sigma x into pi 1 by root r square plus x square. So that E is equal to, the factor E is equal to minus 2k sigma x pi into, if you substitute the limit, that is 1 by r square plus x square. In place of small r, substitute capital R, that is 1 by root capital R square plus x square, and later substitute in place of r, substitute 0, that is 1 by x. So E is equal to minus 2k sigma into x into pi into that value, and E is equal to minus 2 into k value is nothing but 1 by 4 pi epsilon naught into sigma into x into pi. If you remove the negative, then 1 by x minus 1 by root r square plus x square. So here if you see, pi and pi cancelled and 2 cancelled. Finally E is equal to sigma by 2 epsilon naught into x, take it into interior side, then 1 minus x by root r square plus x square. So this is the electric field due to a uniformly charged disk. Okay students, so to find out the electric field due to uniformly charged disk, whatever the steps we followed, once again I will repeat to you. See, initially we take a small portion on the charged disk, that is dr. That small portion having the thickness dr and having charge dq, and with respect to the small portion we calculated the electric field at a point P which is at a distance x from the center O, and later we will integrate to the total portion from 0 to the limit capital R radius. Okay, and that is about the electric field due to the uniformly charged disk. Suppose the disk having the radius infinite, if R is equal to infinite, then what happened? E is equal to sigma by 2 epsilon naught. So if the disk having the unlimited radius, then in that case the electric field with respect to the disk is equal to sigma by 2 epsilon naught. Okay students, let us see the electric potential due to a charged disk. We calculated electric field due to uniformly charged disk. Now we are going to calculate the electric potential due to uniformly charged non-conducting disk. So let us take a uniformly charged non-conducting disk having radius capital R and having the charge, having positive charge, and charge density is sigma. Sigma is charge density. So here our aim is to calculate the electric potential due to uniformly charged disk at a point on the axial line at a distance x from the center O. So that is our aim. So before going to do that, let us take a small portion having thickness dr. This is a small portion having thickness dr and which is at a distance small r from point O. So with respect to the ring having thickness dr, what is the potential at P? That is the initially we are going to identify. Later we will integrate to the total radius. So see, and dr thickness ring having charge dq, small charge dq, and dq is equal to sigma into 2 pi r dr. We know it because sigma is equal to charge per unit area and area is equal to circumference into thickness, that is 2 pi r into dr. And next, what is the potential? dV. dV is equal to k into dq by the distance from here to here is root r square plus x square. So k into dq by root r square plus x square, which is the small potential with respect to the small charge at a point P. The point P is at a distance from the charged ring is root r square plus x square. So that with respect to the small charge, the potential at a point P is equal to dV is equal to k into dq by root r square plus x square. And dq, substitute the value of dq here, k into, in terms of charge density, 2 pi r dr by root r square plus x square. So dv is equal to k into sigma into 2 pi into r dr by root r square plus x square. By integrating on the both sides, k sigma 2 pi are the constants, so we write those constants out of the integration, and 0 to r, this is 0 to v. So let us suppose r square plus x square is equal to z, then dz is equal to 2r dr. So to get easiest simplification, in place of r square plus x square, let us suppose z, and dz is equal to, dz is the derivation of z, dz is equal to 2r dr, in terms of dx that is equal to 0. So that 2r dr is dz. So V is equal to, potential V is equal to k into sigma into 2 pi into integral of r dr. r dr, in place of r dr, substitute dz by 2. dz by 2 into root z by integrating the factor dz by 2 root z. So if you integrate that factor, finally we get the result. K value is 1 by 4 pi epsilon naught and sigma into 2 pi by 2. Take it the denominator 2 outside, and z 1 by root z. So z power minus 1 by 2 plus 1 by minus 1 by 2 plus 1. The limits are 0 to r. So minus 1 by 2 plus 1 is 2. So that 1 by 2, if you, then 2 pi and 2 cancelled, and here also 1 by 4 sigma by 4 epsilon naught, numerator we have sigma, and 4 epsilon naught into 2 z power 1 by 2 whole with respect to limits r and 0. And see, sigma by 2 epsilon naught into z power 1 by 2, z means r square plus x square whole power 1 by 2 is nothing but root r square plus x square, and apply the limits 0 and r. So finally substitute the limits. V is equal to sigma by 2 epsilon naught into root r square plus x square, that is, in place of smaller substitute capital R, and next minus, in place of smaller substitute 0, minus x. This is the potential due to a uniformly charged disk. Okay student, this is the easiest process. Little bit integration we need to solve it. So initially the concept is, we are going to calculate the potential at a point P with respect to the uniformly charged disk. So before going to calculate the total potential, first we take a small region having small charge dq. With respect to the small charge dq, we calculate the potential at a point P, and then we integrate to the limits 0 to capital R. So finally we get the potential V is equal to sigma by 2 epsilon naught root r square plus x square minus x. Okay students, Let us meet with the another topic in the next class. Keep watching. Thank you very much.